Hey, good evening. Hope you're all taking a look at some of the problems I looked up on D2L. We want to look over some of those and whatever else you're interested in. Anything in particular that you want to look at tonight? Tonight is just going to be review for the final exam. So check the final exam schedule here, I suppose. Let's see. We have our final exam scheduled for Wednesday, 5:30 to 7:20. So the final exam information is this. Wednesday this coming week, 1 week from today, 5:30 to 7:20. By email only again. The same as the other tests, open book and notes and calculator. No help from people. All right, it has to be like this. It'll be better in the fall, I think. Very difficult to study on your own. I noticed as the semester went on in some of my classes, people are showing up less and less and trying to catch up on the lecture by watching them later, but then they procrastinate and they get behind. Once you're behind in mathematics, you're lost. That's too bad. I really want you to show up for all the lectures and keep up with the homework. I normally always have homework in this class turned in. I can't turn in papers here, and I get homework by email. It's too many. I can't figure out what class is what. And I just can't. So I'm sorry we couldn't do homework this semester or keep up so much by having class on time. The practice problems on D2L. Let's keep it simple. Let's just say that all problems will be similar to the practice set or the homework problems from the text only since last exam. All right, so I'll keep it real and simple. When I say similar, I mean, I'll give you the same problem with different numbers and different curves and surfaces and that kind of thing. Different functions, so it'd be the same style. But then we can also have homework similar to the homework problems out of the text. Take a look at all those. Come see me online if you have any questions on those. Ask questions tonight if you have them, we'll try and cover them. Any questions on the final exam? Okay, well, I just lost my page, good. Go back to it, marked it and immediately lost it. I could do these in order, maybe. And then as you wish, we can jump ahead a little. I might skip, make sure I get to some of the later ones.
Is cumulative the exam?
Again?
Is it cumulative or is it just gonna be the
Yeah,
last?
the exam's gonna be cumulative. All the problems similar to the practice set, which is cumulative, but it doesn't have everything on there. Or homework since the last exam. So if it's not on the practice set and it's before the last exam, then don't worry about it. I think that's gonna be plenty to study right there. And like I said, on these, I'll just give you problems just like the practice problem, but with different functions and surfaces and numbers kind of thing. So you should see similar wording and all that, but then I'll have some similar to the text also. You don't have to study everything, but you do have to study through the semester. All right, let's try this one then. Sketch the hyperbola and label the foci, vertices, and asymptotes. Abbreviate here. Sketch. Give foci, vertices, asymptotes, if any, of this one. So this is a hyperbola. Maybe on the exam, I'll give you an ellipse, right? Because I'll change the equation so it's an ellipse. That's the idea. Or maybe I'll change it to a parabola. X minus 3 squared, maybe we'll keep it a hyperbola, minus 9y squared equals 36. If I gave you a conic section on there with an equation, how do you do that? Well, you first rewrite it in its standard form as x minus 3 squared over 36, I can write it 6 squared, minus y squared times 9 over 36 is y squared over 2 squared. Equals 1, right? When I divide by 36. So now I observe, since the bigger number is under x, this opens left and right. Hyperbola, because it's x squared over a squared minus y squared over b squared equals 1. If it was plus, it'd be an ellipse. Hyperbola has an equation x squared equals 2py, or y squared equals 2px would be substantially different. Opens left and right. And then we also know that because we replaced x by x minus 3, that translated to the center. So it's not centered at 0, 0. It's centered at 3, 0, whatever's subtracted here. And furthermore, the number under the positive term here, under x, gives a equals 6. And the number under y gives b equals 2. So we can figure this out easily, right? This will be the vertex distance here, a equals 6. And we sketch it like this then. 1, 2, 3. There's the center, 0. I like to sketch it because it actually takes away some of my calculating and avoids mistakes. If I have a equals 6 and it opens left and right, then I just go over 6. 1, 2, 3, 4, 5, 6 to the point 9. And then I have 9, 0 is a vertex. Then I go 6 to the left, 1, 2, 3, 4, 5, 6. And now instead of doing arithmetic, I can do counting, which is sort of arithmetic. And there's another vertex at minus 3, 0. There's the vertices part. Now what about the foci? Well, the foci I can calculate because for a hyperbola, c squared equals a squared plus b squared tells me that c equals square root of a squared plus b squared. Right? That's like the Pythagorean theorem, c squared equals a squared plus b squared. If it's an ellipse, remember its difference. It's a squared equals b squared plus c squared. A is the biggest number for the ellipse. C is the biggest number for the hyperbola. So we root some square, 6 and 2. We've got square root of 40 is 2 square root 10. So there's the distance to the foci. And so I've got here somewhere 3 plus 2 square root 10. C units to the right of the center. And somewhere over here, 3 minus 2 square root 10. Well, square root 10, 2 square root 10 units to the left. All right, now, what are the asymptotes, right? The asymptotes normally are y equals plus or minus b over ax, right? But we shifted the hyperbola. What do we do with the asymptotes for the shifted hyperbola? We just shift the asymptotes too. So if we replace x by x minus 3 in the standard equation here, we replace x by x minus 3 here. And if we shifted y, we'd have to replace y by y minus whatever it was too. Then we get the asymptote equations. So let's see, b and a are 2 and 6. So this is y equals plus or minus 1/3 x minus 3. So these are slope 1/3 going through the point 3, 0. We ought to have it about like that. If we go over 1, 3, we ought to go up 1. This. There's y equals plus 1/3 x minus 3. Here's y equals minus 1/3 x minus 3. Now I've labeled my asymptotes. And finally, I can draw the hyperbola. Each branch of the hyperbola goes through the vertex on its side and approaches the asymptote. I don't expect extremely accurate plots. Make it go through the vertex and approach the asymptote. That's good enough. Don't have to plot extra points and all that. Lots of machines do that very well these days. So there's my hyperbola. All right. With everything labeled. So try that on your own for number 1. You can come back and take a look at this video if it doesn't work out, right? Take a look at number 2. We learned some things with polar coordinates this semester, right? One of them was area. What is the area of one petal of the rose? The equation is r equals 4 sine 3 theta. Well, remember what a rose is, it's just what it says. And we can find one petal of the rose by finding 2 consecutive values of theta where r equals 0. So we have r equals 0. That means we're at the pole, the origin, when, well, what? 4 sine 3 theta equals 0. Right? Which is equivalent to sine 3 theta equals 0. 2 consecutive positions, we can choose our theta equals 0. That makes sine 3 theta equals 0. And then theta equals pi over 3 is the next time. Next greatest value of theta at which sine 3 theta is equal to 0, right? Sine is equal to 0 when you put in 0 for its angle. And it's equal to 0 the next time when theta equals pi. So we need, when its argument is pi, so we need theta equals pi over 3. So here's the beginning and end of a petal of the rose. We can sketch it over here. Here's theta equals pi over 3. And this rose has petal length 4 because the farthest you get from the origin is 4 times 1, right? Sine is between -1 and 1. And so this petal is going out like this, coming back just tangent to theta equals pi over 3. It has to be tangent to the ray theta equals 0 where r is equal to 0 the first time, tangent to the ray theta equals pi over 3 where r is 0 the next time. And it goes out halfway in between at theta equals pi over 6. Figure it out, at pi over 6, you've got 4 sine. Pi over 2 is 4. That's the largest. Right? So there's 4. 1, 2, 3, 4. 4 units out there. There's the petal. And there's 2 more of these also. We'll leave those out. So I'm sorry, there's 5 more of these. This is a 6-petal rose, right? N odd makes 6 petals. And so we'll just take one of them. What's the area there? Well, the area formula is A equals 1/2 integral r squared d theta from alpha to beta, where alpha is where the rate where it starts. Theta is pi over 3 where it begins. Pi over 3 where it ends. And so we're gonna have 1/2 the integral from 0 pi over 3. And the idea is that this is r of theta. R is written as a function of theta. And so we're taking 4 sine 3 theta squared. Theta. That'll give us the area just using this formula. You want to have this handy for the exam in case I ask you the area formula. What might be a nice idea is just write out all the answers to the problems on a practice test, work through all of them, make sure you got them all. And then when you see a similar one on an exam, then just go look up what you did for the one with similar functions and similar numbers. Maybe it'll be. All right. Well, 4 squared is 16 times 1/2 makes 8. I have 8 integral from 0 to pi over 3 of sine squared 3 theta. 4 squared times 1/2 being 8. How can I integrate sine squared? Put a half angle in there. That a lot this semester for some reason. I don't know why. This seems like the examples. Sine squared of 3 theta is also 1 minus cosine of twice that angle by the half angle identity. 3 theta is half of 6 theta. If I write it like that, then I know how to integrate it, right? I'll run it up this way. Now I have 8 times integral of 1/2 is 1/2 theta. Integral of cosine 6 theta is sine 6 theta over 6, right? Integral cosine k theta is sine k theta over k. So I've got sine 6 theta over 6, and then also over 2. So the integral of 1/2 cosine 6 theta is 1/12 sine 6 theta. Well, all that work for nothing because we're going from 0 to pi over 3. If we put in 0, sine is 0. When we put in pi over 3, we get sine of 2 pi, which is also 0. So this is just going to be 0 at both ends. I'll drop it out. And what I have is then 4 theta, plug in 0 and pi over 3 and take the difference. Apparently, I have 4 pi over 3 is the area of 1 petal. Well, we did parametric equations. Want to make sure you can do those. You'll see those again next semester. Want to be comfortable with them this semester. Oh, so I'm sorry, I was looking at number 4. I'll go ahead and do number 4. Find parametric equations for the line that is tangent to the ellipse. 4x squared plus 16y squared equals 32 at the point on it, 2, 1, which you can plug in and see it's a solution. I left out a few words. It's actually asking for parametric form of the line. How can I find the tangent line in parametric form? Well, what do I need to write parametric equations for a line? Remember? Point, and I need a direction vector. So think that when you think parametric line, point and direction vector. What's a point? Oh, I have one. Okay. So this is x0, y0. Now, what's the direction vector? Oh, yeah, the tangent vector is for the tangent line. So I'll say the tangent vector, use our notation here, v for the direction vector of the line, is what? Well, it's dx dt dy dt. So you need parametric equations for the line here, for the ellipse. The parametric equations for the ellipse are r of t equals what? Remember how to parameterize an ellipse? what you can do is rewrite this in the standard form. It becomes x squared over 16 is x squared over 4 squared plus y squared over 2, y squared over square root of 2 squared. So here's our ellipse in its standard form. Now, from the standard form, I can figure parametric equations. X equals, if you have x squared over a squared, it's x equals a cosine theta. So we can say x equals 4 cosine theta. And y equals square root 2 sine theta. How do we know that gets parametric equations? Well, if you take x over 4, you get cosine theta and square it. So this is cosine squared when I take x squared over 4 squared. This one here, when I take y over square root 2, it becomes sine, and so y squared over square root 2 squared is sine squared. So this is cosine squared plus sine squared by the Pythagorean identity is 1. So this parameterization is going to make x squared over 4 squared plus y squared over square root 2 squared equal 1. That shows all these points are on the ellipse. That's a nice way to remember it. I didn't show that it goes all the way around as theta goes from 0 to 2 pi, but in fact it does. Along each axis, you get pi over 2, pi, 3 pi over 2, and 0. So it's not the polar angle, but it is when you're on each of the axes. But now we know that r of t is therefore, because of this parameterization, r of t is 4 cosine theta, square root 2 sine theta. There's the vector valued function that sweeps out the ellipse. Its terminal point sweeps out the ellipse. That being the case, the tangent vector is dx dt is minus 4 sine t. My derivative of this is x, y, and derivative of y is square root 2 cosine t. There's the tangent vector. I should call it theta. Sorry, theta. I call this r of t. I guess I should call it r of theta. So use, and then this is dx d theta and dy d theta. I was using t and theta both. Use either t or theta, right? All right. So I use theta. It comes out to be that. And now v at the point of tangency. 2, 1. Well, this is the point where the coordinates are 4 cosine theta, square root 2 sine theta. What we need is 4 cosine theta equals 2. If 4 cosine theta equals 2, then cosine theta equals 1/2. And what makes cosine theta equal 1/2 in the first quadrant is to take theta equal pi over 3. And then similarly, sine theta becomes square root 3 over 2. This becomes square root 6. Supposed to get 1. Oh, I know I divided wrong. Not good. I divide by 32, I get x squared over 8. So this is 2 square root 2. Sorry about that. Squared. This is two square root 2 cosine theta. So I divide by 32 to put it into this form. X squared over 8 plus y squared over 2 equals 1. Now, that means x equals 2 square root 2 cosine theta. Y equals square root 2 sine theta. Theta going from 0 to 2. And now I've got to say at 2, 1. I've now got the point. 2 square root 2 cosine theta and square root 2 sine theta equals 2, 1. So apparently from the first one, I get that 2 equals 2 square root 2 cosine theta implies cosine theta equals 1 over square root 2, which is also square root 2 over 2. That means theta equals pi over 4 to put in the first quadrant and get 2, 1 in the first quadrant. And then we can check it on the second quadrant, put in square root pi over here, we get square root 2 times 1 over square root 2, sure enough gives 1. So now it's right. It always helps to check your answers. See? Otherwise, you get to the last step and have to do it all over. So this is the point where we want the tangent vector, theta equals pi over 4. And we want v at pi over 4. So v at pi over 4 for the tangent vector is, let's see, minus 4 sine pi over 4 from this statement up here. Square root 2 cosine pi over 4. There it is. Well, sine pi over 4 and cosine pi over 4 are both 1 over square root 2. So this becomes minus 4 over square root 2 becomes minus 2 square root 2. And square root 2 times 1 over square root 2 is 1. So there's the direction vector. I can call these the little a and little b from our direction vector. Now I've got x0, y0, and a, b. I can immediately write the equation for the tangent line. For those, x equals x0 plus at, y equals y0 plus bt are parametric equations for the tangent line. The easy ones to write where you just write linear equations. So this one is 2 there plus a is minus 2 square root 2. B y0 1 plus bt plus t. There they are. And you can leave out the middle part. X equals 2 minus square root 2 square root t. Y equals 1 plus t. Gives me the tangent equations to the line. Not enough questions. Feel free to take your mute off. I hope that volume's up high enough. I think I can hear you if you talk. All right. There's a tangent line. Assuming this records, I'll put it up on D2L and you can listen to it again if you want. Then I'll ask the questions too. Did you want to look at number 3 where you find the volume of the parallelepiped? Is that good? Yeah. Okay. Look at number 3. Find the volume of a parallelepiped. This review stuff is really, really good. It really makes it sink in. That's what final exams are for, is to help you remember in the long run. Find the volume of a parallelepiped with vertex at the origin and 3 edges of that parallelepiped emanating from the same point, the origin. Given by u is 3 minus 2, 1. V is 0 minus 1 minus 3. And W is 0 to 1. How about this one? the thing to remember is that the volume of a parallel pipette is just the triple, the scalar triple product, right? That absolute value. So the volume is absolute value of U, V, W. Sometimes they put comma between them. Where this means U dot V cross W. It's just a additional notation. Since this comes up so often, they give this notation to this. And remember how we can calculate that? We can, there's nothing wrong in the final with calculating this cross product and then calculating this dot product. But what's even faster for the scalar triple product than calculating cross product with a determinant followed by the dot product? This one. These bars mean absolute value. But the triple scalar product is also the determinant, where you put U in the first row, V in the second row, and W in the third. Remember that one? It's been a while. So you just put 3 minus 2, 1, 0 minus 1 minus 3, 0, 2, 1. That determinant. And then this is an absolute value, so I'll put absolute value here. ABS is the computer word for that. So it doesn't look like 2 bars on each side, and then it'll look like a norm or something, a link of a vector. All right, so there's a notation conflict, straight bars for absolute value, straight bars for determinant. But now we can calculate this. We want to calculate the absolute value of, and remember how to calculate 3 by 3 determinants. We take this number, multiply it by the subdeterminant wiping out its row and column. Minus 1 times 1, minus 2 times minus 3. Then minus this element, wipe out its row and column, take 0 minus 3, 0, 1. Well, this is 0 times 1 minus 0 times minus 3. And then plus the last element in the first row, wipe out its row and column and take this determinant. Right? 0 times 2 minus 0 times minus 1. Well, look at that. These two are just 0. Minus 1 plus 6 is 5 times 3 gives me 15. Absolute value leaves at 15. Yeah. So the volume of the parallel pipette is just 15 cubic units. If you were to sketch this vector, write it without sketching those exactly. The idea is that you've got 3 vectors out coming from the origin or whatever point. These two and make a parallelogram. You take these two and make a parallelogram. And then you make a third parallelogram by connecting those. And then you can make parallelograms out of what's left. There's a 6-sided figure. The special case is a 6-sided die when all these things are squares and meeting at right angles. Well, how about this? Find the distance, this is number 5, from the point to the line. See all the neat geometric stuff we learned how to do in 2- and 3-dimensional space? This tangent line here, you could have done in calculus 1 since it's doing an ellipse, but if you put this in 3-dimensional space, you can now do tangent lines in 3-dimensional space, and that would have been impossible back then. And this is still a nicer way in 2 dimensions frequently. So we learned a lot of geometry this morning. Here's number 5 then. Find the distance from the point with coordinates 4, minus 2, minus 1 to the line L given by parametric equations x equals 2 minus t, y equals t, b equals 1 plus 2t. Boy, I wish I had one more day to review. We could probably finish this. All right, how about that? What's the distance from the point to the line? This is tricky, right? There is actually a formula for this. Tempted to write down if I think I remember it. I believe it looks like this. It says that the distance, when you have, well, actually, no, I'm sorry, let's not, I don't think we did that. Let's do it like this. When you have point P and a line L, the way you can do this is to take a point Q on the line, any point whatsoever, and now you take the point from P to Q, well, either way, P to Q, just to go from the smaller letter to the bigger letter. And then you take the orthogonal projection of this here, the length of that one is your distance. A lot of these, if you draw them out, you can figure out how to do them, right? How did I do that? Well, I know the length of this one right here, this vector right here, is the projection of PQ onto the vector V in the direction of the line. So if I have vector V moving along the line, then I take the projection of PQ onto V, and it gives me the shadow of PQ. I guess I should say it's the other way. PQ and go this way. All right. And then this one here, let's erase this for the moment, I'm out of room. So that this one is PQ minus the projection of PQ onto V. There is another way to do this, as I said, but I think for what we've done, this is probably the easiest way. That's what this vector is, and what we want is the distance at the length of this vector. The length of what we call the orthogonal component vector of this vector PQ. So we just have to do that computationally. First, find the projection of PQ. Well, what's PQ? We subtract the coordinates, right? What's an easy point on the line? Whatever you want. Pick T equals 0. That's really easy. I'm less likely to make a mistake. So point Q might be 2, 0, 1, right? The constant term. Put in T equals 0, you just get 2, 0, 1. There's an easy point. Any T you want. And now PQ is 4 minus 2, I'm sorry, 2 minus 4, the coordinates of Q minus the coordinates of P. 0 minus the negative 2. And 1 minus negative 1. Now we take the projection of that onto V. What's V? Well, V, the direction of the line, is the numbers that multiply T here, right? This is X0 plus AT. This is Y0 plus BT. This is Z0 plus CT. A point on the line, X0, Y0, Z0. And the direction vector, ABC. So A must be minus 1, B is 1, and C is 2. So it's minus 1, 1, 2. By reading off the numbers that multiply T. So that's the projection I'm going to take. And how do I compute that? Remember, I take the dot product. Let's write it one more time. It's the projection of minus 2, 2, 2 onto minus 1, 1, 2. And the way you do that is projection of V onto U is V dot U over length of U squared times U. Right? So we'll take minus 2, 2, 2 dot minus minus 1, 1, 2, over length, minus 1, 1, 2, squared, times the vector, minus 1, 1. So there's the projection vector, this one right here. Nice that picture is. If you draw that out, that really helps with a lot of stuff. Well, dot product is this times this, 2, plus this times this, 2 more, plus this times this, 4 more, it's 8. 2, 4. Now, what's the length of this vector? It's square root of 2 squared plus 1 squared plus 1 squared is square root of 6. But it's squared, so it's actually 6, right? So length squared is just this squared plus this squared plus this squared is 6. And then times the vector, minus 1, 1, 2. So this is the vector, minus 4 thirds, 4 thirds, 8 thirds. There's the projection, this one. Right? Now, how do I get the distance? I compute the distance. My formula over here is the length is PQ, which was right now again, PQ minus the projection. Copying that of PQ onto V. Length, right? So PQ is this vector, minus 2, 2, 2. And the projection was minus 4 thirds, 4 thirds, 8 thirds. What's the length of that vector? Let's see. Minus 2 plus 4 thirds is minus 6 thirds plus 8 thirds is 2 thirds. Minus 6 thirds plus 4 thirds is minus 2 thirds. And then 6 thirds minus 4 thirds is plus 2 thirds. And 6 thirds minus 8 thirds is minus 2 thirds. It is. You can root some square of these, that's just fine. You know what's easier? Since everyone's multiplied by 2 thirds, rewrite this as the length of 2 thirds times the vector minus 1, 1, minus 1. Yeah. And remember, that's equal to 2 thirds, or absolute value of 2 thirds is 2 thirds, times the length of the vector minus 1, 1, 1, using our theorem of scalar multiplying a vector is the absolute value of a scalar times the length of a vector. This one is like square root of 3, so we've got 2 over 3 square root 3 makes 2 over the square root of 3. There's the distance between the point and the line. Okay. A lot of different things this semester, I think. This is the longest, hardest part of the course. Next semester, it's a little shorter. More complicated, but I think it's actually a little not quite as fast paced. I hate to do this one. This is a long one, but maybe I can shorten it a little. Rotate the coordinate system, the principal axes, what they call them, to remove the xy term, I said. Then name the conic section. Rotate and name conic section. One thing you should remember out of this course is after linear equations, the next simplest equation in 2 variables is an ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0, and you can identify always either a conic section in the degenerate case or no solution by rotating this and completing the square in the result. This one, we won't have to complete the square because there's no x and y terms in here. We'll just have to rotate it. So I give it a little bit easier on this practice test. But how do we do that? Remember the rotation equation? You can look it up in the book. I think it's nice to have it handy, like if you've done your practice test problems, then you have it written all down already. If you have A, B, C, the coefficients of x squared, xy, and y squared, it's cotangent theta, cotangent 2 theta equals right, over A minus C. Find out if that's right. Which would then be minus 1 over 1 minus 1. Cotangent 2 theta equals infinity. In this case, you turn it over and you write it as, when you have a division by 0, what you're really saying is tangent 2 theta equals 0. So you get cotangent 2 theta is undefined. Well, if tangent is equal to 0, tangent 2 theta is equal to 0, what does that tell you? You can pick any angle for which this works. But we'll choose then any angle theta that makes tangent 2 theta equal to 0. So let's choose 2 theta equals it's A minus C over B. Yeah, I'm sorry, it's A minus C over B. I wrote this upside down. I was clustering at that. Yeah, it's A minus C over B. So I don't have to switch in that case. So it's 1 minus 1 over minus 1 is 0. Yeah, cotangent to 2 theta is A minus C over B. This means that we could choose any angle 2 theta that works. Well, we know that the cotangent is cosine over sine. So what we want is cosine equal to 0, so the quotient's equal to 0. Well, the first time the cosine is equal to 0, so we choose the smallest angle possible, is when its argument is pi over 2. So I'll choose 2 theta equals pi over 2, so the cosine will be 0, which tells me that theta is pi over 4. I need to rotate this 45 degrees. I could also choose 3 pi over 2, and then I get 3 pi over 4 here. That would work. Any angle that makes cotangent of 2 theta equals 0. All right, if I choose theta equals pi over 4, then I have the following equations for the rotation. X equals x prime cosine theta minus y prime sine theta, where the primes did not denote derivatives, they denote the new coordinate system. I like to use x hat and y hat, but the book uses these, so I'll stick with these. Y is x prime sine theta pi over 4 plus y prime cosine theta. Well, let's see, this cosine and sine of pi over 4 are both 1 over square root 2. So this is just 1 over square root 2 x prime minus 1 over square root 2 y prime. And this one is just 1 over square root 2 x prime plus 1 over square root 2 y prime. Pretty easy on this one. There's the substitution I need to make to get rid of the xy term. The whole purpose here is Then I can complete the square in other cases. I don't even need to in this case, and recognize the conic section. Plug those in. This original equation star. And I get x squared is 1 over root 2 x prime minus 1 over root 2 y prime squared minus x times y plus y squared. Minus 2 equals 0. There it is. Now let's see what happens when I multiply this out. Boiling this, I get 1/2 x prime squared plus twice this times this is twice times 1/2 is 1 minus 1 if you like, x prime y prime, and then plus 1/2 y prime squared. That's this one. Then this one, I just get a minus b times a plus b. That's the difference of squares. So this is 1/2 x prime squared minus 1/2 y prime squared. When I FOIL this one, and the two cross terms cancel. And this one, using FOIL again, is 1/2 x prime squared plus x prime y prime plus 1/2 y prime squared. All minus 2 has to add to 0. And something nice has happened, right? This one cancels this one. It better, otherwise we chose theta improperly, right? The purpose of choosing theta to be that value is to make these cross terms cancel. Now let's see, I got 1/2 minus 1/2. Just by luck, these two cancel. And I'm left with 1/2 x prime squared. Then 1/2 y prime squared minus 1/2 y prime squared. These two cancel. Plus 1/2 y prime squared minus 2 equals 0. Well, I can rewrite this as x prime squared plus y prime squared equals 4. What's that? Particularly easy conic section, it's a circle actually. Right? Well, this is a circle of radius 2. Wait a minute. No, I didn't do this right. These two don't cancel. I thought this was not looking right. No, it helps to know where you're going. This is 1/2 y prime squared. I got to fix my answers as I go here. This is why I say check your answers, right? 1/2 y prime squared. This is plus 1/2 y prime squared again. These don't cancel. Plus another 1/2 y prime squared. This should have been 3 y prime, 3/2 y prime squared here, right? This one plus this one plus this one is 3/2 y prime squared. And now I've got x squared plus 3y squared equals 4 by multiplying through by 2. Not a circle. If I divide this by 4, instead I recognize x prime squared over 2 squared plus y prime squared times 3/4 is the same as y prime squared over 2 over square root 3 squared, right? 1 over square root 3 squared gives the 3. 1 over 2 squared gives the divided by 4 equals 1. So divide by 4 and write it by that, like that. Now you recognize it's an ellipse with a equal to b equals 2 over square root 3. The bigger number a says that you have semi-major axis equal 2 in the x prime direction. And here's what you draw. Theta is the rotation from the xy system to the x prime y prime system. So I rotate pi over 4. That splits the axes. Here's pi over 4 for theta. And then along this axis, the x prime axis, this axis, y prime axis, I have the semi-major and semi-minor axes. So a is 2. I go out 2 units. 1, 2. about to this direction, 1, 2. There's my vertices, and then I go 2 over square root 3 the other direction up here somewhere. It's 2 divided by 1.7. It's a little bigger than 1, right? So this would be 2 over square root 3 out this way. Minus 2 over square root 3 y prime coordinate here. And here's my ellipse. Here it is. That's a little longer one.
How many problems do you anticipate will be on the phone?
Oh, you know, I meant to mention that. I want to make it a little shorter. I want to make it so you can do it about like a midterm. So I think about the same length as the midterm, right? So like probably 3 pages. I haven't written it yet. But that way you have time to check your answers on this one. Sometimes if we're getting a little rushed on the midterm, I'll make sure I don't do that in the final. Right. Find the distance between the parallel planes. How about that? That one does have a formula. And there is a formula distance from a point to a line, but I don't think we covered it. So I was showing you how you can do these general parametric problems. You can figure out the formulas. I'll skip that one and move on to the next one. So I got out of some of these. If you want to see that, we can do that. But you do a projection again, but there's a formula that looks like A times x0 plus by0 plus z0 plus d over root a squared plus b squared plus c squared. There's a formula for that. When you have a point on a plane and a normal vector, you can do distance from a point to a plane. So you just pick any point on the one plane, take its distance to the other plane, where the plane is ax plus by plus cz plus d equals 0. Put it with the d on this side. Gives you the distance formula from a point to the plane. Then you can use that to find distance between 2 planes. All right, so that, but you can figure that out also if you don't have that formula by just doing the same thing, do a projection and onto the normal vector. You can take the 2 planes, take 2 points on the plane, so you can draw yourself a vector PQ. This is the other way if you don't have a formula. All you have to do is say, well, here's the normal vector. The distance between the plane is the length of this vector, which is the projection of PQ onto the normal vector. Well, the normal vector is just ABC, right? If the equation of plane is x plus by plus cz plus d equals 0, the normal vector is always the letters ABC. You just read them. It's not harder than that. So you take the projection of a point from one plane to a point on the other, PQ, and then you project that onto ABC, and that length then is the distance. Anyway, so that's another way to do it. You can either use the formula or you can compute this projection like we did. Okay, so we sort of did that one, right? All right. Now, number 8, identify the quadratic surface. What is it? And sketch. Okay. Identify and sketch. Let's just do A here. X equals y minus 1 squared over 4 plus z minus 2 squared. Or the trick is to recognize those 6 different forms for quadratic surfaces. Which one is this? Right? It looks kind of like something we've seen before. Remember one looks like this? Z equals x squared over a squared plus y squared over b squared. What was that? This one? This was the elliptic paraboloid. That looks like this, but with z and x interchanged. And the thing translated, 1 in y and 2 in z. So what we say is this is also an elliptic paraboloid. It's got the same form, just translated and interchanged the variables. So there's the identify. Now, how do I do the sketch? Well, its center is where you translated it. You didn't translate x, so it's still at 0. Y is at 1. I call it center. Let's call it for the elliptic paraboloid the vertex. And z is at 2. So 0, 1, 2 is where the vertex is, because you translated it so. And now a is equal to 2, and b is equal to 4. But see, this opens upward on the standard way. So this one with x on the left-hand side opens about the x-axis. About the positive x-axis, because this one's open up about the positive z-axis. So it's going to look like this, or not x, not positive x direction, I guess I should translate it. So I put the center at 0, 1, 2. So 0 in x, 1 in y, 2 in z. I go to this point right here in the yz plane. I put the vertex right there. And I draw an elliptic paraboloid coming out. It's got b and c equal, so it's actually a circular paraboloid when these two, I guess you call them a and b, when a and b are equal. So instead of calling it elliptic paraboloid, I'll call it circular paraboloid when a equals b. And we try and make these cross sections here circles. Coming out of the point 0, 1, 2 in the yz plane, you've got circular cross sections and it comes out of the board like that. I don't expect a fancy sketch there. Find the vertex and make it look like a, headlight or something coming this way. It's easy to do a cross section. Just insert the z equals 1 plane, put z equals, I guess, the x equals 1 plane, and put 1 equal this, and you see immediately, oh, it's just a circle, and you figure the circle, right? And it's easy. That's radius 2. So if you put in the x equals 1 plane, you get a radius 2 circle. Plug x equals 1. Well, in the beginning, we did a whole lot of Taylor series. Suppose we do number 10 here. Yeah, I guess. Suppose I find the Taylor series at x0 equals 1. Actually took up a long time, but it was a long time ago. For f of x equals e to the 2x. Amazing how much material we do in this course. What do we do? For the Taylor series, it's f of 1 plus f prime of 1 times x minus 1 plus f prime of 1 over 2 factorial times x minus 1 squared plus so on and so forth. You can also write it in sigma notation. I think that's what I asked for this problem, actually. So you can either do sigma notation or you can write it this way and then figure sigma notation from it. Let's see, what do I ask here? Yeah, I said use sigma notation. Let's just write in sigma notation. You can do this and figure it out also, but it's sum k equals 0 to infinity. The kth derivative of f at 1 over k factorial, where 0 factorial is 1 at this one, x minus 1 to the k. Right? Now I have to figure a formula for the kth derivative of 1. So I look at this and I say, if f of x is equal to e to the 2x, then f prime of x is easy. It's 2e to the 2x, right? Here to e to the kx is k e to the kx. Then f double prime of x is the second derivative of that. The derivative of this is 4 or 2 squared e to the 2x. F triple prime is the derivative of that. Is twice that is 2 cubed e to the x. And so you then observe that f of 1 is e to the 2. F prime of 1 is twice that, so it's twice e squared. F double prime of 1 is 2 squared e squared, and so on. F kth derivative, just following the pattern of 1, is 2 to the k e squared. There it is. So my sigma notation for this one is sum k equals 0 to infinity, 2 to the k e squared over k factorial x minus 1 to the k. There it is. I should do some of the more recent stuff with the little time I have left here, huh? Sure we're ready for that. Awful lot of stuff on here. Oh, let's do this. I forgot to do this. We did not get to some of these things last time. Delete the following problems. Should have said this at the beginning. I didn't get to them. Delete number 16. We didn't cover the unit tangent, unit normal, and unit binormal. Those are useful for differential geometry. They probably won't see them. Again, you'll mention them in calculus 4, but just briefly, they're easy to compute actually. And then I didn't get to talk about curvature, which I really did wish I got a chance to talk about. I was thinking I'd give an extra credit problem on that one. But curvature is actually useful, and we weren't able to talk about that one topic that I did. And we can delete. Let's delete 16, 17, 18, and 19. I should send an email to confirm that. All right, now let's do something that we did do. I'll make it a little easier for you. On number 20, find the arc length, something we just did, of the parametric curve R of t equals 2 cosine ti plus 2 sine tj plus tk. Letting theta run from 0 to t running from 0 to pi. What the arc length of that curve is. Remember the formula we derived last time? We did the proof for that, the limit of the, or the derivation, I guess you call it, derivation of the definition. By taking the limit of those line segment lengths and calling that the arc length. This is actually the helix, right? Because this, it goes around the circle of radius 2. 2 cosine, 2 sine, executes over circle of radius 2 in the xy plane. Tk, not t to the k power, sorry. And then if you have a later function of t, at plus b, this makes a spring shape because it spirals up like that. So you have, this starts when t equals 0 at the point 2, 0, 0. And it lies on the cone, the cylinder, excuse me, of radius 2 because its projection in xy plane is a circle of radius 2. But it increases linearly with t, so it's going up like this in the counterclockwise direction because it's t is the polar angle here. As t increases, c increases, so it goes up, up, up this way. It's a spring shape like that, and we're going from 0 to pi. We're only going to take the arc length from the, remember t is the polar angle in xy plane from here to here, 0 to pi. So it's this piece of the spring around to the back side. what is that arc length there, L, 1/2 of a loop of the spring? So it's like the problem we did last time. We'll say that this is, the arc length is integral from A to B, or A to B, of the square root, well, the easy notation is to say the length r prime of t, dt. I like this one because it holds in any number of dimensions. In 2 dimensions, it just reduces to this square root of dx dt squared plus dy dt squared. That's the length of r prime, right? R prime has component dx dt dy dt. And for this one, t is going from 0 to pi, so this goes from 0 to pi. Well, what's x and y? Here's x, that's whatever multiplies I. Here's y, that's whatever multiplies j, and here's z. Oops, and I'm sorry, I left off my dz dt. This is in 3 dimensions, I forgot for a second. Plus dz dt squared dt. Integral from 0 to pi of the square root of, well, dx dt is minus 2 sine. dy dt, derivative of this one is 2 cosine. And dz dt is 1. There we go, we just have to integrate that. So I picked a Cook's problem here. Usually this is very hard to calculate analytically. You just estimate it on a computer because that integral of the square root is usually too hard. But in this case, I've got that integral from 0 to pi. Let's see, this stuff here is 4 sine squared plus 4 cosine squared. 4 sine squared plus 4 cosine squared is 4. So it's 4 plus 1. dt. Oh, it's just square root 5. Integral from 0 to pi dt. Well, this is just t evaluate pi and 0, take the difference, it's pi. So it's square root 5 pi. There it is. There's an arc length of half a loop of the helix. That's the simple example. How about this one for the last problem? Then I'll go back to the series here. This is number 22. Look at A, so this is the harder one of the two. Suppose I take sum k equals 1 to infinity. Remember how to do these? 1 over k plus 2, k plus 3. I think this one might cause some trouble is what I'm doing. Wonder what that sum adds up to. Have to evaluate what it adds up to. What do you think? There's only 2 kinds of sums that I'm going to ask you. What is the sum of it? Either a telescoping series or a geometric series, or some multiple one plus multiple of the other. Those 2 kinds, and they're multiples, sums of multiples of them, linear combinations of those. Well, this is either telescoping or geometric. It's not geometric. A geometric series is a series that looks like this: a plus ar squared plus dot dot dot. It looks like sum a times r to the k running from 0 to infinity. Those, you know, sum to a over 1 minus r. You write the formula, you have it immediately. So be able to do those. See this, or you see this, be able to add it up. The telescoping series is a little harder. What do? When I see this, I write it in partial fractions. I say 1 over, I have to put here, k plus 2, k plus 3, adds up to some number over k plus 2, plus some number over k plus 3, right? I wonder what it is. Well, if I take 1 over k plus 2, if you work the partial fractions, you can use the expand button on your calculator, or that works, I think, on Symbolab too, or you do it by hand, just multiply through by k plus 2, k plus 3, and get 1 equals a times k plus 2, k plus 3, plus b times k plus 2, right? and solve this, and what you get is A equals 1, B equals minus 1. So it's just- Yeah. And so you get that this is actually equal to 1 over k plus 1 to minus 1 over k plus 3. Now the series adds up to, I started at 1 here. I'll try to go to start at 0. Yeah, that's right. And so I'll put in k equals 1 here, and I'll get 1 over 3 minus 1 over 4 plus, when I put in k equals 2, 1 over 4 minus 1 over 5 plus 1 over 5 minus 1 over 6, all the way up to dot, 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 1 over, if I take the nth partial sum is what I want, Sn equals sum, k equals 1 to n, not to infinity. I added up here of over k plus 2, k plus 3 is therefore this sum, and I stopped at 1 over n plus 2 minus 1 over n plus 3. I deduce from that that Sn, since this cancels this, and this cancels this, and this cancels something in here, and this will cancel something in here, this all adds up to 1/3 minus 1 over n plus 3. That's the nth partial sum, Sn, right? So what's the sum of the series? The sum of the series is S equals the limit as n goes to infinity of the nth partial sum. That's the definition of the sum of the series. Well, that's the limit n goes to infinity of 1/3 minus 1 over n plus 3. But 1 over n plus 3 is driven to 0, right? As n goes to infinity, so it's just 1/3. There it is. End of the semester. Hope you had a great one. Come back and see me next semester, I hope. Get to see your faces. All right, thank you so much for being in my class, and I'll be online and ask me more questions online. Thank you.